All right, so we wanted to illustrate how high spatial temporal resolution, which is unique to small satellite imagery, may have an advantage when we monitor marine debris, which is highly dynamic, keeps moving around due to currents, weather, vessels, and the model objective was to investigate the contributions of the shape versus spectral characteristics in the feature selection process. So we'll see in a few slides that marine debris aggregates have a common shape due to ocean current and front conditions. We also lastly wanted to investigate applicable spectral indices using PlanetScope imagery. And we know that PlanetScope has only 4 bands at the moment, red, green, blue, and NIR. So there were not a lot of options because spectral indices, the main one that's being currently used is called the Floating Debris Index on Sentinel-2, and it has the shortwave infrared band, which was not present in PlanetScope. So we were limited to RGB and then other indices like NDVI and vegetation indices. Really, you want to add anything?
Yeah, just really briefly on that. The choice of imagery was actually quite a key component of this research because most of the prior work was focused on using Sentinel-2, which is 10-meter spatial resolution with a much more impressive spectral resolution, but also a less impressive temporal resolution. And as our Ankur alluded to, the features that are our target are characterized by a very dynamic environment where they're moving in time and space very rapidly, as opposed to something that's static and like on land. And so for us, having that high spatial resolution, high temporal resolution were huge competitive advantages and something that really had not been explored in prior work. Especially coupled with a deep learning approach. So, and then our choice of deep learning architecture is also something that plays in favor of a rapid deployment approach as well, which we'll discuss in a short moment. But I just wanted to kind of paint a picture a bit more why we chose this imagery and why it's very important to the goal we were trying to achieve. Okay.
So, thanks, Lily. Yeah, definitely. Okay, so first step, of course, was creating the data set. So the first step was conducting a literature review of plastic and marine debris detection studies. When we started, there were not a lot of studies that were done using satellite data, and especially which had ground truth data. The main 3 ones were done by Dr. Lauren Bierman at Plymouth Marine Laboratory. And then the main one, which we used data from, was on the Bay Islands of Honduras, where they did validation using boat expeditions. And they found a lot of data using Sentinel-2, but they didn't have the tile ID or anything. They just had the date and the tentative location. And so we had to locate marine debris on the Planets Explorer tool. And the way we found it was co-locating whatever dates we found from the paper and the tentative locations. And then we saw the Explorer marine debris locations, and we also verified by using like a manual time series. So we saw whether marine debris locations were changing in a week's time, in a few days' time, and that temporal nature of marine debris flow kind of confirmed that these are the locations which we need to label. And one more thing is our definition of marine debris in this case was quite loose. We did not focus only on plastics because we cannot see from just RGB NIR what is plastic, what is not. So these are aggregates of anything that's floating on the ocean, whether it's vegetation, wood, algae, plastics, anything that's floating on the ocean that is flowing dynamically is floating debris according to this project.
And that is likely to carry as a carrier for plastic, something that would aggregate.
Carrier plastic, right, exactly. And so we co-located these observations, and we identified 65 planet scene IDs, PlanetScope scene IDs, and 1,300 debris patches. And in parallel, we also collected river discharge images, thinking we might use it. We haven't yet, but these are discharges of debris from rivers due to flooding or heavy rainfall or such events. And we labeled this using NASA Impact's image labeler tool. So we hand annotated each of these debris aggregates. Of course, that's a slow process, tedious, but but we created this data set. And these images are in process. So we did label everything else that you see unlabeled, but this is just to show what was being labeled and how it looked like. So yeah, these are the way we labeled was we made sure to cover each debris patch in the sense that the long diagonal of the rectangle fit inside or completely covered the debris patch. So you can see the length of the diagonal is the longest length that is covered by the marine debris aggregate, and that's how we chose to label each of our aggregates, because we focused on an object detection model that Lily will talk about in a few moments. And if you want to click on this link as well, I'm not going to do that, but it shows you some patches found on the ocean surface that are marine debris in Honduras, and most of these locations were in Central America, Guatemala, Honduras, as well as some in Ghana, but mainly Central America.
And those patches, well, that link actually, if you in your free time want to check it out, that actually is the images that are in this article are correlated with the dates that are captured in our training data set. So it's essentially a validation of the study in which we derived these coordinates and timestamps from, with like very close handheld camera visuals. And in that, you'll see a bunch of like seaweed, algae, and plastics all intermixed into these aggregates. So it's a form of, it's a bit of a form of validation for.
Yeah, definitely. So yeah, now I'll hand it over to Lily to explain the tiling and serialization.
Yeah, and one more comment on why we chose object detection, because back when Ankur and I first started this project, I mean, this field is relatively nascent. There were no ground truth data sets that really existed in a geospatial sense for knowing where marine debris, let alone plastic, was tagged in the ocean, and that matched with like actual like satellite imagery. There was only one, and it was released by the University of the Aegean, and it was very small, like 5 data points, and it was only used as a validation for another study. So there was no ground truth data, no labeled data for us to work with. So we only had 6 weeks actually to
Initially,
complete this discovery phase of this project. And nominally for an approach like this, if you look at the features, this would be very well suited for a segmentation problem. However, since we had to create the data set ourselves to train the model, it is orders of magnitude faster to create bounding boxes around the features rather than a granular segmentation of the features. So that's another reason why we chose object detection, because the curation of the training data is a lot faster.
Right.
So once we had the bounding boxes labeled, the next step was to start thinking about how to get them into machine learning ready format. So that requires the larger PlanetScope images to be cut into smaller pieces to make it actually feasible to ingest into a machine learning workflow that's utilizing like X type of resources. Say it's like a single GPU. There are memory constraints on the amount of imagery or the amount of data that you can provide to a process. So basically, like without getting into the weeds of why we tile our imagery, we had to tile the imagery, and because we had to tile the imagery, we also had to tile the associated labels, which are bounding boxes. And so development team created a very efficient tool for this many years ago called Label Maker, and that's what we used to tile both the imagery and the labels. And it is kind of like it leverages Slippy map coordinates. So for us, there's like a bit of a conversion of raw imagery spatial resolution to what is it? Sorry, like a OSM, like a Slippy map zoom level, which is the closest one to approximate PlanetScope spatial resolution is zoom level 16. So we tiled our imagery and labels in this way. And the output of Label Maker is essentially a bunch of tiled images with Slippy map coordinates at the approximate same spatial resolution of native PlanetScope imagery. And the labels are stored in a compressed array format. and it's in a very suitable state. It's almost like a data frame of the labels, the coordinates of the labels, like image-specific coordinates of labels, the label classes, and the image arrays. And it's in a perfect state to serialize into TensorFlow records. So that was essentially the last step to get the data into model-ready format. So we can probably move to the next slide. And actually, the one thing we did before this, you can leave it on this slide. The one thing we did before this, of course, is partition the data into training, validation, and testing components. And basically, we did about a 80-10-10 split, and we subsampled every single PlanetScope imagery, PlanetScope scene used in our data set to make sure that we didn't bias the training, validation, or testing partitions to any specific conditions associated with given PlanetScope scene, because there's a lot of variability, there's a lot of heterogeneity in PlanetScope imagery with respect to the color space, as well as, of course, like the non-imagery specific things like cloud cover, ocean surface conditions, stuff like that that you really need to make sure you apply a sampling scheme that crosses like your entire data set. So we subsampled for each partition from every single scene, and we'll get into the augmentations in a moment, but basically now talking about the architecture that we used, we played in favor of a balance between accuracy and speed in our selection of the object detection architecture. We use something called RetinaNet, and it's a state-of-the-art object detection architecture that is widely used in the Earth observation domain. And it's a single stage object detection architecture, which is plays in favor of speed with respect to some of the more nominal object detectors, which leverage a two-stage approach, where in the first stage, bounding boxes are proposed, and then in the second stage, only bounding boxes that have passed, a certain threshold gate are then classified for object class. Essentially, that's in the nominal architectures, that's a two-stage process, and single stage detection networks like RetinaNet, that's all compressed into one stage, where essentially you have a feature extraction network, then you have two, which is right here, we'll discuss that, and then two classification heads, one which regresses the bounding boxes that are proposed, and the second one which classifies the objects within those bounding boxes. Each of these has their own loss function to do it. But basically, just to briefly talk about what's going on this side, the feature pyramid network is a huge part of this, and it's basically this can be any backbone architecture like ResNet, MobileNet, anything that is essentially taking an input image and applying convolutional layers and producing output feature maps like this. And essentially, like a feature pyramid network produces feature maps at multiple scales for a given input image. And what that allows for is essentially a mapping of features at different scales. So different levels of information are captured in each of these different scales. Starting at the bottom, you have what you normally see in the initial layers of a convolutional neural network, like lines, very crude features like lines and edges, and those start to become more abstract as you move up the feature pyramid network. And eventually at the top, you have the most abstract representation of the features in the image. And so this is the high level feature map. And then what's happening, this is the bottom up path. This is like the feed forward. If you think about like a neural network, this is the feed forward computation, and then coming back down here. This is essentially where we're taking these feature maps and we're actually applying these lateral connections, also known as, some might recognize this as a skip connection. And we're actually taking the semantic, we're combining the semantic information from the feature maps with, one important thing. What's happening here in this top-down path is essentially the feature maps are getting hallucinated to a higher resolution to restore back the original dimensions of the input image. And so in that hallucination process, you imagine that a lot of interpolation could lead to a lot of like poor artifacts, and poor localization, because there's been so much subsampling and now downsampling happening. So a lot of information could get lost. These skip connections allow for that precise localization from the less sampled layers on the upward path to actually be combined into these final resolved features in the top-down path right here. So the final output is essentially feature maps that have strong localization information, and these are used for both of these two classification heads. The first classification head, or let's talk about the bounding box one. The bounding box classification head is essentially looking at the activations in these feature maps. And one of the big things that a single shot detection network leverages is essentially this notion of all objects in the real world can fit within some given set of aspect ratios and scales. So instead of starting from scratch and learning these scales and aspect ratios and then proposing bounding boxes to fit objects ad hoc, single shot detectors start with like a default set of bounding boxes of X number of aspect ratios and scales. Those are applied onto the feature maps and essentially given in the training process, given a score for intersection over union with respect to the ground truth. And only those default bounding boxes that pass a certain IOU threshold, say it's 0.5, are actually then passed to the classification head here, where the bounding boxes are actually regressed to fit or to most closely approximate the ground truth bounding box. So the predictions get regressed to match the ground truth. And so that's how you essentially get to the point where you have like a final closely matching set of bounding boxes, which then go through the last step called non-maximal suppression to remove any duplicate detections for a single object. And then in the other classification head, and this is happening simultaneously, in the other classification head, that's where we're essentially computing like cross entropy, between the classes that get predicted for each bounding box, and measuring the loss of the predicted class with respect to the ground truth class. And one thing that RetinaNet is that actually RetinaNet improves upon these other single shot detection networks is that it uses focal loss. And focal loss allows for explicit hard negative mining because it applies. So it's essentially focal loss is basically cross entropy plus like a tuning parameter, and that tuning parameter helps the learning focus on difficult examples and deprioritize easy examples. So that in the case of like a single class problem like us, like for us, like the only class we had was marine debris, that allows the model to spend less time focusing on what is background and more time focusing on what is foreground, because there's a huge distribution like imbalance between foreground and background in our data. So focal loss had a huge role here, and it's also something that addresses a problem between single shot detection networks and two-stage detection networks, because two-stage detection networks apply like sampling heuristics that do that foreground to background offsetting in another way. So this is an alternative to that. Cool. Next slide, please. These are just some of the key parameters. We use the TensorFlow Object Detection API. There's a lot of development around that, and a lot of different architectures implemented. I'm sure some of you have probably used it, but this is, and so you might be familiar with what we're seeing here. These are a few snapshots of the model configuration file, and I've only taken a few like key things out of it right now. And just as a reminder, the repository is open source, so you can go look at this model file if you want afterwards. We have a link at the bottom of these slides. So as I said, we applied a single shot. This is synonymous with RetinaNet, single shot detector with a feature pyramid network. Our background was ResNet 101. The activation function that we used was ReLU 6. ReLU 6 is essentially ReLU with that's with a limit of 6 applied, and that's based on empirical reasoning that's described in the ReLU 6 paper. Don't need to get into that here. RMS prop optimizer, which is essentially like very strong. It's an unpublished optimization function, but it's an adaptive optimization algorithm that addresses the issue where you have huge variance in the gradients, and it's very difficult to use a single learning rate for your entire data set, and you're using batches instead of like a full batch approach, which is very rare. You don't ever really feed your data set in as a single batch. So usually you have this like gradient variance between batches, and instead of using a single learning rate, RMS prop actually only looks at doesn't look at the magnitude of the gradient for each batch. It essentially looks at the step size and then modifies the step size, and that helps address like the gradient variance problem. That could be a long discussion that I'll save for you guys to look at afterwards if you'd like. And then in terms of augmentations, we applied pretty nominal ones like horizontal flip, vertical flip, adjustments on the brightness and contrast, and then slight crops to the image. And this was only applied to about 50% of the samples, just randomly sampled. Okay, next slide. So the model was trained for 50 epochs, and we went through a few different iterations, changing a few hyperparameters, adding and subtracting augmentations. And our final model produced an F1 score of 0.74, which is okay for iOS, excuse me, F1 score. F1 scores can be pretty tricky to achieve high score for. So this was a good starter. And as you see here, this is essentially like a depiction of some of our predictions. Like essentially what you see is the class label. We are in one class, Marine debris, and the confidence of that prediction. Cool, next slide. Yeah, we don't have to spend time on this, but essentially like what we're seeing, well, maybe the one thing that I'll note here is that, as we mentioned, there was a bit of a common geometry to the aggregates that we really didn't know, we didn't expect when we first started this. But that's not always the case. There's a lot of like little fragments of larger, maybe like if you zoomed out, this would be part of a long linear aggregate. But if you look at them close up, some are very much so like disintegrated into little pieces like this. And we actually had, a priori, we really thought like there were going to be a set of features that would present strongly as false positives, such as clouds, wakes, waves, vessels, islands, like little islands that resembled like the color and maybe shape of marine debris aggregates, because what we didn't mention here is that like these marine debris aggregates in some areas, like some areas of severe pollution, can extend upwards of like, you know, 1 or more kilometers in length. So they can be absolutely massive. And what we found is that, at least in our test data set, and our whole data set at first was very much so biased to the Bay Islands of Honduras, because that's where most of the prior studies had provided ground truth reference for. And of course, there's like not necessarily a very pressing problem for cloud coverage, or, you know, or well, yeah, mostly that. I don't want to say water turbulence, but also wakes and waves. You don't really expect to see a lot of that in the Bay Islands of Honduras either. So those really, we did have representations of cloud coverage and more turbulent surface conditions. And we obviously had other areas included in our data set, but those presented less at the end as false positives than we had initially anticipated, which was very cool to see. Can you go back up, actually? Just one more up, maybe? Yeah, so for, you know, for example, but also I just wanted to say that vessels were actually surprisingly not vessel activity didn't seem to be much, you know, as robust in the Bay Islands of Honduras as it did in the latter areas that we tested the model on. So at first we didn't think they were much of a problem, but they definitely showed up when we tested in other areas. Okay, next slide, please. Next slide. Wait, yeah. So the output of this model are geospatially naive bounding boxes. So they're essentially just coordinates that are specific to the tiled image. So if we want to actually like use these bounding boxes in a geospatial sense to get like area measurements of these debris aggregates, or like, you know, do other, you know, geospatial you know, operations with them, we have to get those back into, we have to get the geospatial metadata back. So essentially that's when we use the slippy map information, which is like zoom coordinate XY. And it's in a different like spatial coordinate system than we typically think of. So there's a conversion process to get that back into, let's just say, like, you know, WGS 84 projection. And so we have developed like an entire process to do that. And then we save those out as a GeoJSON format that you can actually overlay back onto your Planoscope imagery or base map. Cool. Next slide. Ankur's going to take it from here.
Sure.
We'll jump later.
So yeah, as we mentioned in the objectives, one of the objectives was to investigate spectral indices for detecting marine debris and see if it operates better than, or gives a better accuracy than just RGB imagery. So we collected near-infrared band 4 imagery from the same PlanetScope scenes we labeled, and explored appropriate indices, and finalized 3 that could possibly be used. And we had a model-ready NIR dataset as well. But we identified sensor-derived and spatial registration offsets. So there were geographical offsets between the NIR band and RGB, and I'll show that in a moment. So this offset, of course, led to complications in learning and even accuracy. So we'll see what happened. Sorry, one second. There we go. Okay, so band 4, well, the RGB sample and the corresponding 8-bit and 16-bit channel near-infrared image, in this case, you can see that they're pretty well aligned. And I would say about a third to a half of the scenes had this sort of arrangement where the geographical offset was not there, or extremely minimal to notice. But many scenes in the same data set, you can see that they had a heavy geographical offset where the RGB data was not matching up or not aligning with this corresponding NIR data. And this is because over the open ocean, planets calibration they don't have ground truth data points to validate the NIR and RGB. They're collected separately. And we even contacted Planet's team to give them this notice that this is an issue, and they're aware of it, and they currently have no method to fix this over the open ocean. So this we could not use the NIR bands because there was no way to correct this offset for aligning the RGB and NIR. And were they aligned, we could have tested the model on NIR and seen and compared the accuracies as well. So this issue of geo-registration prohibited us from trying NIR. And then we did, before we observed that, we did investigate other indices, specifically the Modified Triangular Vegetation Index and NDVI, of course. And these were the main indices we could use, along with maybe EVI or like other vegetation indices, because we only are playing with RGB and NIR. And again, had the NIR dataset been perfectly properly aligned, we could have used these indices and then trained our model over RGB, NDVI, MPVI, and NIR separately. So yeah, really anything?
Yeah, and so one of the big advantages that we really wanted to use the NIR for is that part of the spectral signature of plastic does lie in the near infrared. It's predominantly in the shortwave infrared, but there is a section of the near infrared that falls. And NDVI is actually, like, sounds very surprising that we wanted to use that for this problem, but what it actually helps with is to spectrally unmix the other materials that are composed in these aggregates from plastic, because obviously, like, the organic materials like kelp and driftwood, stuff like that, will have a reflectance in NDVI where plastic won't.
Right.
Okay.
And many of the samples we did investigate were also containing high amounts of algae and sargassum. And sargassum was a big contributor to marine debris in the bay lines in Honduras in the tropical Caribbean waters. So that's another reason NDVI shows up well in this index.
Yeah. Okay.
Right.
So our model was trained on imagery examples from the Bay Islands of Honduras, Durham, South Africa, Accra, Ghana, very small, fractions from these other areas outside of the Bay Islands of Honduras. We included the reference points from the University of Aegean, and those are in Mytilene, Greece. And I think a few other examples off the coast of Scotland. So there was an effort to include geodiversity in our training data set, but it was really not up to par with where we would like it to be. But that said, we wanted to test the model for its generalizability to other areas of interest. So the next step, after we developed the model and we got evaluation metrics for our test data set that's specific to those other areas I just mentioned, was to do a little bit of literature review, journal review, stuff like that, to identify other hotspot areas where plastic pollution, debris pollution is a major problem. And it mostly happens to be around areas that have a major river outlet to the coast. And that's also why, by the way, we collected river samples, because they're major source to sink locations for the debris that you see in these coastal areas. And by the way, planoscope imagery doesn't collect imagery over the open ocean, but that's okay for what we're trying to do, because the only stuff we expect to see at 3-meter spatial resolution are these macroplastics and stuff that's consolidated in these marine debris, aggregates, and that's only happening like in coastal areas, because as these aggregates travel offshore into the open ocean, that's when you have the erosion of the plastic, of plastic into microplastics and smaller particles. And that starts to be very difficult to discern in satellite imagery. So that's why coastal imagery is very sufficient for this problem. So the first the first two areas, the first area mainly here that we focused on was the Sidram River, and that's in Jakarta Bay in West Java. It's kind of known as like the most polluted river in the world, and it's depending on, especially during like the rainy season, debris aggregates are very visible in 3-meter spectral resolution imagery. So if you want to go to the next slide. We applied our trained model on planet-scope imagery that was captured during the rainy season in for this area of interest. And one of the things I wanted to make sure of was anything that we detected, I wanted to make sure was ephemeral and not some static feature that existed, in consecutive days. So I explicitly pulled consecutive days worth of imagery to validate, before and after scenes. And some of these, like I said, it was around the rainy season, so you would expect maybe like there would be rainfall and then, debris transport from the Sidram River to the coastal area, and you'd have, significant like representation of these features in the before after day. So these are just a few examples of detected aggregates and before and after scenes. There are two rivers. There's the Sidram and the Ciliwung River. It's a smaller river outlet in Jakarta Bay. But that's. I'll move on to the next, for the sake of time, I'll move on to the next AOI.
And just quickly mentioning that this part of temporal change that you see just a day or two apart, where the discharge debris is there and not there, that's also part of the labeling process where we discern whether it's debris aggregate. So it's a good example. All right, go ahead.
This is a further illustration of that, before and after. This is the geo-rectified detections in the red boxes. So GeoJSON format. Okay. I did do essentially like a bit of a QA on the detections from the Sidram River predictions, and then basically use those as an extension or an augmentation of our original training data set to improve geodiversity as like another iteration. We don't need to talk too much about that. And there are evaluation metrics that are on a follow-up slide. I guess actually the one thing I didn't mention there is that was another AOI. Briefly, this is the Pasig River outlet in Manila Bay in the Philippines. And as you can see, like the debris issues, like pretty drastic. Again, this is also in the rainy season, and you can see a lot more vessel activity in this area. And these long linear vessels, like, were in some cases quite problematic, depending on like the reflective color of them. If they're more of a warmer color, they were easily confounded as debris aggregates. So that means that in follow-up iterations, like I would explicitly like classify for these false positives. Like I wouldn't just do a single class approach. I would actually like include classes for vessels and other confounding features, because essentially modeling for false positives directly allows you for the model to like learn the schema associated with those classes. And it's more informative than just bucketing it into a background class and making that background class really complex and hard to learn. Okay, next. So these are the evaluation metrics that I generated after testing the model on new AOIs, taking the predictions, QAing them a bit, incorporating those into a new model training iteration, and then gradually testing this on newer, locations. And as you can see, the performance really drops in new areas. So for us, this is just extraordinarily informative on what sort of next steps would need to be taken to make this a globally generalizable model. Okay, next please. The last area of interest was actually not something that has surfaced in the literature at all. It was kind of just brought up by a fellow teammate at NASA Impact. He is working on a different project, and somehow this area on the south coast of Spain came up, and it's basically an area of intensive hydroponic agriculture. Yeah. Plastic greenhouses, intensive greenhouse farming. And so when you look at it, this satellite image, all of this white stuff right here is actually those are plastic greenhouses. And so when it rains, and this is all loose soil, it's a very arid climate, as you can see, and so the soil is very loose. And when there is rainfall, a lot of the remnants of these plastic greenhouses are not like very strong structures. They're very weak. It's not a very. It's actually there's like social issues associated with this area that you can read about. It's actually really interesting. There's like a whole ethic, humanitarian, dilemma to the working situations in this area. And so the infrastructure is very poor, and so when it rains, like these plastic greenhouses are definitely like affected, and any residual of them gets carried into the coastal area. And so we applied our model actually after somebody brought this to our attention to see if we could actually detect anything with our model. We applied it to planetscope imagery of, I think, 2 dates. And a few things were detected. And of course, this is all like theoretical, hypothetical, marine debris. We don't know. This could also be other things like convergence of other things, but like, essentially just candidates. But yeah, that was the other geodiversity study that we did. The next slide. There's just a few other examples. And that's the kind of thing you expect to see. You expect to see them, any plastic, any marine debris converging in these areas where you have like that color difference is essentially telling you that there's like some convergence dynamic happening there. The last thing that we wanted to do is like, okay, we can't use the near infrared from planetscope imagery, and it doesn't have the shortwave infrared, 2 things which are very important to actually parse out plastics. So can we do can we try something like sensor fusion with imagery that does have that spectral information, and take the detections that we derive from planetscope imagery and use the imagery information from the other sensor, if we can co-locate it spatially and also like temporally, such that we can see the debris aggregate in the other imagery, and then use the spectral information from the other imagery source to get a more refined signal of plastic. So our options were limited, but we tried, after conversation with like other scientists in this domain who were all utilizing Sentinel-2, we decided to try this approach with Sentinel-2 imagery because it does have that spectral information, albeit a much lower spatial resolution.
I'll just quickly mention that we did co-locate 26 Sentinel-2 tiles from our data set of PlanetScope. So we have 26 tiles that did match within a 2-week time frame of these, and we need to check whether like this debris will be shifted because they're days apart from the PlanetScope imagery. But yeah.
So this effort has been tabled a bit due to other project work, but it's part of our next steps is to actually progress on this spectral and mixing approach to get a further refinement of our understanding of the presence of plastic in the detections. So I think that leads us potentially to the last, the last slide before the links. So our current and future initiatives, we want to improve dataset geodiversity for the reasons that we just discussed, and continue to train a more geographically generalizable model. We'd like to develop a spectral mixing workflow to validate the presence of plastic in the detected aggregates. This will require, since the time that we've initially worked on this, of course, PlanetScope now has other spectral bands. Those are mostly focused on agriculture applications, so they don't yet work for this particular problem space, but we hope that maybe even like in the future, PlanetScope imagery will have the spectral information that we need to do the spectral mixing without the need of sensor fusion. Scaled model deployment and inference with web. Is this basically like if we're developing a model that's made for rapid monitoring and alerting, we need an interface that people can access to scalably like run the inference on their area of interest, or have it monitoring an area of interest with daily revisits kind of in real time. So that's another like future step. And the last thing is transitioning from object detection to semantic or instance segmentation. And this will help us, of course, refine our area measurements for the detected marine debris, but also helps us address a problem that is unique to object detection in this domain, in which like for an aggregate that's upwards of like a kilometer or more in length, that's going to span across multiple of our tiles. How do you intelligently conjoin the bounding boxes that are predicted across tiles for one aggregate that's super like that's a massive aggregate in terms of its length? It's difficult to do with object detection, and that could be absolutely like removed as a problem entirely if you're using semantic segmentation, where you're actually simply just joining pixels of the same digital number across tiles. The joining problem is actually very straightforward. So we didn't know that these aggregates would be that long. So this is definitely something that encourages semantic segmentation even more. And instance segmentation is just an extension of semantic segmentation, where if you had like multiple segments detected in a scene, if you want to have like segment 1, segment 2, segment 3, like instance ID associated with each, it's just it's a bit more informative than nominal semantic segmentation. So Ankur, would you add anything else there? Okay.
I would just say we are currently a couple of researchers from European Space Agency to do this increase geodiversity and also co-locate Sentinel-2. So yeah, it's work in progress. Here's our contact emails and GitHub and Dataset. So if you want to check this out, all of this is open source. So feel free